All right, guys. So next unit, we are in Unit 8. This one will actually go by pretty quick. So the packet that you received in class today, that consists of 8.1, 8.2, 8.3, is going to be your first quiz. So 8.1 through 8.3 will be your first small quiz. So we're going to break this unit into smaller quizzes. If we have time, we'll do a unit test at the end. I still don't know yet. So let's get right into it. So the first section in 8.1 is this idea of finding the average value of a function on an interval. So we know that the average value, just like taking the mean, right, is your you're finding the average. I don't know how else to say it. All right, the mean value theorem for integrals. So if f of x, if you remember the mean value theorem, aka MVT for derivatives, but now we're going to be doing this for integrals. All right, so the idea when we were doing this for derivatives, so just a little side note, when we were doing this for derivatives, we had said that there is a value, a derivative at some point, so there's a slope that is equal to the average slope, f of b minus f of a over b minus a. This was the mean value theorem for derivatives that said there was a instantaneous rate of change that is equivalent to the average rate of change somewhere within that interval. So we're kind of doing the same thing, except now we're using it for integrals. Well, we know that integrals is about area, okay? So the mean value theorem for integrals says if f of x is continuous on a closed interval, so again, just like the MVT for derivatives, these two things have to be checked. Is it continuous and is it on a closed interval? Then there exists a number c in the closed interval such that the area under the curve from a to b of f of x is equal to f of c times b minus a. And then we can take this one step further and we basically say that f of c is equal to the integral from a to b of f of x dx divided by b minus a. Right? Same equation, just a little different. So this is very different than average, sorry, this is the mean value theorem, aka we're going to call it the average value theorem, but we'll talk about this in a little bit. Okay, but the mean value theorem says that the area of the area under the curve of f of x is going to be equivalent to f of c times b minus a. So here's our visual demonstration of this for integrals. So we have this graph of f of x, which is negative x squared plus 8, is shown below. The area under f of x above the x-axis and between x equals 0 and between x equals 0 and x equals 4 is calculated to be approximately 21.3. So this area right here is 21.3. So what the mean value theorem basically says is that the value c exists between 0 and 4, right, such that f of c times b minus a is equal to this 21.3. So there is some value c that if we plugged in here, and we divided it by 4 minus 0, it will equal the area under the curve. That's basically all it's saying. So if we know that the area under the curve was 21.3, well, there's some value C here, which they have already solved for us to be 2.3. If I went up to that point on the curve and found the area from 0 to 4 with a height of f of c, right? Because that's our height and that's basically our width of this little rectangle. That area underneath f of c is equal to 21.3. All right, so let that sink in for a second. So a vitally important byproduct of the MVT for integrals is what we obtain when we solve for f of c. The result is outlined on this next page. And what's important is this idea of average value of a function. If f of x is integrable, that means you can actually integrate it on the closed interval from a to b, then the average value of f of x on that interval is 1 over b minus a times the integral of f of x. And that is equal to the average value. All right. The average value, which is, we're going to call it f of c still. Okay. Now, the nice chunk of these problems will be, we will use a calculator for, but it's basically saying that if you find the area under the curve and you divide it by the closed interval, b minus a, you're getting the area under that curve, right? So let's do an example. Let f of x equal 12x e to the negative x. Find the average value of f of x on the interval from 2 to 5. So we know that the average value equation is equivalent to 1 over 5 minus 2 times the integral from 2 to 5 of f of x, which is 12x e to the negative x. So if you take out your calculator and do this in the calculator, so actually put this into your calculators, you will get an answer of approximately 1.4623. So what you just solved for is basically what? What does this 1.463 look like? What is that telling us? So what that is telling us right here, I'm going to try to graph what I got in my calculator. So the graph that we just graphed looks, or f of x equals 12x times e to the x looks like this. It's not the best graph, but this is what you guys should see on your calculator. And what we solved for here is, let's call it f of c, right, from the mean value theorem for integrals. So we solved for the y value, okay, 1.4623. We solved for the y value on that graph. And by solving for the y value, I'm basically saying that if I found the c value for this y value, which in this case is going to be 3.2983 because you can do that on the calculator. And this is 1.4623. The c value that will give us 1.4623 should give me the area under that curve. That is the average value of this function. So how do we find c such that the average value is equal to f of c? So how do we find c? Well, I know that 12x e to the negative x, the average value of that function from 2 to 5 is 1.4623. Now, on the interval from 2 to 5, right? That is important because it's not going to be 1.4623 on a different interval. Well, with a calculator, you can set these two equal to each other and solve for x, or you can graph this and graph this, right, and find that cross point, and you get that x is approximately 3.298. All right, I'm going to leave number 2 for you guys to do, right? This is a you do. This one, you should be able to complete this one without a calculator. Okay? No calculator. I know that they show you the graph here and the answer, right? But try to do this without a calculator. Find the average value. And then find the value of c guaranteed by the MVT for integrals for the above function. Because remember, this doesn't give you c. This just gives you f of c. Okay? So that just gives you f of c. And then you have to actually solve for c. All right, next example. Got milk. The cows on a small dairy farm in northern Indiana are milked in the morning during a 2-hour period. Milk from the cows are pumped into a storage tank, and the volume of milk in the tank at time t is modeled by a strictly increasing twice differentiable function where m of t is measured in gallons. So it's a strictly increasing twice differentiable. So that basically tells us that the function is continuous and differentiable. M of t is measured in gallons and t is measured in minutes. At time t equals 0, there are 300 gallons, okay, of milk storage. Values at selected times of t are given in the table. So let's estimate m prime of 70, which basically means what is the derivative? Using this table, let's estimate the slope of m at 70. So this is just asking for the average slope. Now, from a table, you can't make up your points. So I know that 70 is approximately right here, right? So I'm going to use those 2 points. So m prime of 70 is going to be approximately m of 90 minus m of 50 over 3360 minus 1640. Oh, I don't know why I did that. Sorry, that's on top. Minus 90 minus 50 equals, well, m of 90 is 3360 minus 1640 over 40. You do the math and you've got 43 gallons, approximately 43 gallons per minute. Well, let's use the data in the table to evaluate the integral from 0 to 120 of m prime of t. So the integral of the derivative. Okay, so you got integral of the derivative. And remember FTC? When you take the integral and you derive it, you're basically left with just the function itself. So using correct units, interpret the meaning. Well, the integral of the derivative is just going to be m of t from 120 to 0. Now this is a little different than the FTC, right, where you have x. So we're not just plugging in x. You actually have to plug in these points right here. So this is going to be m of 120 minus m of 0. You do m of 120, that's easy from the table, 4250 minus 300. And that gives us 3950 gallons. So using correct units, interpret the meaning. So what is this? Well, it's telling us that 3,950 gallons of milk have been added to the storage tank from 0 to 120. Have been added to the storage tank from t equals 0 to t equals 120. Okay. All right, last part of these notes. Using the right-Riemann sum with 4 subintervals, indicate by the data in the table to approximate the average value, 1 over 120, of the integral of 0 to m of t. Now, we cannot use the average value function here because we don't have a function for m of t. We don't know what m of t is. But we know that the integral from 0 to 120 of m of t is the same thing as saying find the area under the curve. And when you don't have a function and you only have a table, you're going to use Riemann sum. So we're using a right Riemann sum in this case. Okay, that's a little flashback into previous section, right? So we're using a right Riemann sum with 4 subintervals. So right Riemann sum means that we are focusing in on our right points. So we're going to ignore that first point. So that's going to be 1 subinterval from 0 to 20. From 20 to 50, from 50 to 90, and from 90 to 120. And it might make it easier if you graph the points if you can't see where I'm getting these values from. So we have the integral 1 over 120, the average value from 0 to 120 of m of t dt using Riemann sum. Therefore, we are approximating. So 1 over 120 is coming along for the ride. And remember, Riemann sum is just a rectangle, right? So from 0 to 20 is 20 times the height. And because this is right Riemann sum, we're going to ignore the 0. So the height is going to be at 780 plus the next one. So the base is from 20 to 50, so that's 30 times the height at 50, which is 1640, plus from 50 to 90 is 40, and the height is 3360. So 40 times 3360, plus from 90 to 120 is 30 again, and the height is 4250. And just do the math. So when you do this math, you got 1 over 120 times 20 times 780 plus all of this, you should get 326,700, which leaves you with 2,722.5 gallons. So the average number of gallons of milk in storage from t equals 0 to t equals 120 minutes is approximately 2,722.5 gallons. Now, this approximation is an overestimate because we are using a Wright-Riemann sum approximation that is increasing on that interval. So if you know that the function is increasing, that means it's a concave up function because it is increasing on that interval. And when you are making a Wright-Riemann sum with a concave up function, right, it is going to be an overestimate. So this is an overestimate because they told us at the beginning the function is increasing on that interval. All right, that's it for section 8.1. It should be pretty easy. We are going back to mean value theorem just a little bit, and we'll explain this a little bit more. We'll talk a little bit more about it in class tomorrow.